in the last class we were discussing the derangement problem. So now, we described the problem in the last class. For instance, we can consider the derangements of 1, 2, 3, 4, right. So the derangement, some derangements I can write, for instance, I will write like this to make sure what we mean. So because each permutation will be written like this. So I can start with 2, I can give a 3 here, I can give a 4 here, I can give a 2 here. This is a derangement because in the ith position we don't see I. So 1 we have 2, the second position we have 3, third position we have 4, and fourth position we have 2, or another one I can write 3, 4, say 4, 3, 2, 1. This is also a derangement, right, because we never get in the ith position. If you look, we are getting a number which is different from I, right. So the question now we are going to address is how many derangements are there. So as usual we take the universe, consider a universe, namely the set of all permutations, set of all n factorial permutations, right. This is the universe. So cardinality of U then is obviously, cardinality of U is equal to n factorial, right. Now what we do is we define the properties which we do not want, undesirable properties. The property P1 is that the at the first position, we see 1, right. So the permutation is such that, say the pi is a permutation, pi of 1 equal to 1. Similarly P1, P2, P3, Pi will be defined as pi of I is equal to I. The ith position we see I, right. So similarly the last Pn is the last property, pi of n is equal to n, right. So the what we are interested in is the set of permutations such that those permutations does not satisfy P1, P2 or Pn, right, easily formulated, right. So that let AI be the set of permutations such that the permutations in AI does not satisfy Pn. Right. Then now what we are interested in is A1 complement intersection A2 complement intersection AN complement, its cardinality. Clearly that means the permutations where the first position does not have 1, the second position does not have 2, and like that nth position does not have n, which is exactly the derangements, right. This is what we want to find, what is the cardinality of this. We can use inclusion exclusion principle, and so the answer will be cardinality of U minus n choose 1 into say cardinality of a single one. See for instance we can use the formula. So here I will say that this is the special case where when you consider T sets out of K sets, their intersection depends only on T, not on individual which T sets we take. So therefore we can use the formula correspondingly. So in this case A1, for instance, what is that, first position is fixed, that means in the first position we see 1. How many permutations are there like that? Clearly the first position we have to give 1, there is no other choice. So therefore n minus 1, but remaining n minus 1 positions you can get any permutation of the remaining n minus 1 numbers. So that is n minus 1 factorial, right. So and this is true for any AI, right. The cardinality of any AI is going to be n minus 1 factorial. Why? Because in the ith position you have to have I, in the remaining positions we can take any permutation. So, if you remove that I, and in the remaining positions we take any of the permutations of the remaining n minus 1 numbers. So, therefore, this is n minus 1 factorial here, and then plus n minus 2 into n minus 2 factorial. Why is it so? Because once you want to fix any 2 so you are saying that how do I say that property Pi and Pj together are satisfied? So, how many permutations satisfy? That means in the ith position we have I, and in the jth position we have j. The 2 positions we have only one choice each. So, in the ith position I have to put I, in the jth position I have to put j. So, in the remaining n minus 2 positions I can take any permutation of the remaining n minus 2 numbers. So, property Pi and Pj are together satisfied. That means the cardinality of Ai intersection Aj is going to be that n minus 2 factorial, right. Similarly, the cardinality of Ai intersection Aj intersection Ak, 3 things together, right, that is n minus 3 factorial, right, because 3 positions and ith position and in the jth position and in the kth position you have to have I and j and k respectively. The remaining n minus 3 things can be permuted in any n minus 3 factorial possible ways, right. So, that is the these are the possible permutations, right. So, how many? So, now this of course this does not depend on which ij position or which ijk position we are talking. So, it is always n minus 3 factorial for any 3 positions we fix, right. So, therefore, we can go to this formula, right. So, we get universe is n factorial. So, when you fix one position, that is n minus 1, choose n minus 1 factorial, and when you fix 2 positions, that is and choose 2 ways you can fix those 2 positions, and n minus 2 factorial, and then we have in 3 positions can be fixed in 3 ways. So, n minus 3 factorial and so on. So, that is minus 1 raised to n minus n factorial, because if all the n positions are fixed, then there is nothing to be done, because it is only one permutation, namely 1, 2, 3 n, same, right like this. So, this permutation only will be there in the last. This is just 1 with whatever minus or plus sign, whichever sign we are ready to give, right. So, then yeah, and then this is the value we get for the dearrangements. We will write dn for the number of dearrangements of 1 to n, right. When we among the permutations of 1 to n, dn things have this property, namely none in the ith position we do not see I, right. So, this can be simplified by taking n factorial out, right. So, this is actually 1 minus, this is what, n into n minus 1 factorial by 1 factorial. So, n into n minus 1 factorial will be again n factorial, right. So, this is n into n minus 1 factorial by 1. So, we can I will do one thing, I will simplify it first and then right. Let us take a typical term. This is n into n minus 1 factorial by 1, that is n factorial on this turns out to be n factorial itself. I will write here n factorial, right, and this is what, this is n into n minus 1 by 2 factorial in fact divided by n minus 2 factorial, right. So, when I combine this and this here, so this will become n factorial, that will be n factorial by 2 factorial. So, this entire term is n factorial by 2 factorial, and what is this? This is you know, n choose 3 into n minus 3. So, we have n minus 1 into n minus 2 in the top in the denominator, sorry, in the numerator, divided by 3 factorial in the denominator. We have n minus 3 factorial here, right. So, here we multiply all these things, we get n factorial divided by 3 factorial, and each term will be, so now ith term will correspond to, so the n into n minus 1 into up to n minus I plus 1 divided by I factorial, and here will be minus 1 raised to I of case. So, into we have an n minus I factorial here, right. So, this when you combine these terms with this, we get n factorial above, and this will become minus 1 raised to I into n factorial by I factorial, right. So, so what we see is this will simplify to that dn is equal to n factorial minus n factorial by 1 factorial plus n factorial by 2 factorial plus, sorry, minus n factorial by 3 factorial, and so on till minus 1 raised to n factorial by n factorial, right. You see here the last term is yeah, n minus 1. So, it was just 1, that will become n factorial by n factorial, right. So, now n factorial can be taken out. So, this will be n factorial into 1 minus 1 by 1 factorial plus 2 by, sorry, plus 1 by 2 factorial and minus 1 by 3 factorial and so on, minus 1 raised to n 1 by n factorial. This is what we will get, right. This is the formula. So, then this will remind us of a formula which we have studied in calculus. So, namely e to the power x is equal to 1 plus x square by 2 factorial. So, the expansion of e to the power x. So, expansion of e to the power x, it will be like this: e to the power x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial. This is an infinite thing, right. Now, what will happen if I put x equal to minus 1, if I put x equal to minus 1. So, e to the power minus 1 will be equal to 1 minus 1 plus, this is x square, right, minus 1 square will be 1 by 2 factorial, and this will be another is minus, because x cube will become minus 1 cube, that is minus 1 by 3 factorial plus 1 by 4 factorial minus, and so on. This will be an infinite with alternating signs, and exactly this is what we see here, but only n terms are seen, right. So, we can say that as n becomes large, this is approximately equal to n factorial into e raised to minus 1, that is n factorial into n factorial divided by approximately equal to. You see that if it is n is greater than equal to 7 or 8, it is very close. You can just do some computation and see it is already getting very close. After some time, see when n is reasonably large, this difference between n factorial by e and n fact this formula will be very less. This is always, yeah, of course. So, the infinite series we are just approximating it by discarding the remaining terms, because as you can see as n becomes large, 1 by n factorial kind of terms will be very small, right. They are not going to affect the total sum much. So, that is why we say that, right. So, the derangements will be dn will be approximately equal to n factorial by e. So, this kind of a formula will be useful in when we find the probability of certain things. For instance, one can ask what is the, in the first question we discussed, the gentleman came to the party, they placed their hats on the table, while going away they took their hats, right, some hat they took and went away. So, what is the probability that nobody will get their own hat, right. This we can say that 1 by e will be the probability if the distribution is uniform. That means each person has the same probability of taking a given person has the same probability of taking any of the hats, right. So, that means all the permutations are equally possible, right. In that case, so 1 by E will come. So, let us not get into the technical details of that. So, because we are not doing probability now. So, intuitively if you understand the ideas of probability, so it will be useful to know this formula. So, in such situations, right. So, 1 by E, right. Now, we will not discuss more than this about the derangements. There is interesting material, but then probably this is not the time and to discuss about them. So, we will move to the next topic, because we have spent enough time on inclusion exclusion principle and examples, right. We have covered a lot of interesting and important examples also, right. So, now we will get into the next question, namely the recurrence relations. The next, because counting problems, this of course, so we have seen several methods now to count and get some information about the combinatorial, to answer combinatorial questions, counting questions. Recurrence relations is another technique which you can which is very useful, because many times in the underlying counting problem we see such relations. The technique is very simple. We just see that the counting problems as such, for it is not necessarily that it is just one problem, it is a sequence of problems. So, there will be some problem for each n, usually most of the time. It is not that it comes isolated. Yeah, not that it comes isolated. So, it may happen that our count is f of n when the underlying problem has a parameter n, right. So, therefore, the solutions corresponding to the n can come as a sequence of numbers, right. So, and we are, so from up to now whatever you have studied, like in okay, even in your 12th standard you have studied sequences. For instance, some of the more important things you have studied about sequences, I mean one of the more popular sequences you have seen are, say for instance, the ones which have there is a common difference. For instance, you start with 1, 2, 3, 4, this is a sequence. So, here the first term, you add one term to the previous term, then you get the second term, right. So, this is an arithmetic progression we have seen. So, you know the formula. So, you know the nth term is obtained by the n minus 1th term plus 1 here, right. So, of course, you need not start with 1. So, you can start, the sequence can be like this: A1, A2, A3, A4, like this. So, here you write An like An minus 1 plus some constant k, right. This k is the common difference. So, this kind of progressions you are very familiar with, and some other kind of progressions, and we will definitely need to know, of course, what is the first number. This is the very important thing, right. We need to know what is this. Once you know this thing, with this formula we will be able to figure out what. For instance, if you give this as 10, then this will be 10 plus k, and this will be 10 plus 2k, and this will be 10 plus 3k, and so on. So, the, for instance, nth term will be 10 plus n minus 1 into k, right. So, that is the good thing about this kind of relations. So, you can infer what is the nth term, right, somehow. So, so therefore, and the another kind of sequence we are very familiar with is the geometric progressions. So, there, so we have sequence like A1, A2, A3, A4, etc., where An is some q times An minus 1, right, q times An minus 1. We need to know what is A1, then we know A2 will be A1 times q, A1 times q, A3 will be A2 times q, that is A1 times q square, and so on, right. Like that we can figure out all the values, right. So, of course these are sequences given with that property, but many times in combinatorial problems we can identify such a sequence occurring, right. So, we can probably see that see when like the problem has a parameter n, and then we already know the values for the answer for the problem when the parameter is n minus 1, right, or n minus 2, then we can say n minus 2, n minus 3, etc. We can find the solution for the problem with parameter n by combine from the solutions of the for the smaller parameters, right. So, let us consider probably one of the most famous problems of this sort, which was proposed by Leonardo of Pisa, right. This is about Fibonacci sequences. So, he proposed this problem. So, we have a pair of rabbits, one female, one male. So, what they do is they put the two rabbits in a cage. They will have a special cage for the rabbit, and then this when they are born, after every month, I mean the first rabbits are there, after 1 month they will produce a new rabbit, right. And then those two rabbits, right, but they produce one female rabbit and a male rabbit, and then they take this female and male rabbit and put in another cage, right. And of course the first month they won't produce new ones, but the second month again they will, second month onwards they will produce a pair of rabbits which is one male and one female, right. And we want to know after n months, nth month, how many rabbits will be there. This is the question, right. So, here we will say that the first month we will write as f0, the number of rabbits at the 0th month is 0, and f1 as 1 because we have initially 1 rabbits, and f2 is such that after, so this one pair of rabbits produce a new one, that is sorry, they produce at the second month only, not first month. So, this will be 1 only, right. But f3 what happens is we have these existing rabbits are there, they will not die, right, and then they will also produce. So, for instance 2 months before, which how many rabbits were there, those many rabbits will, those many pairs of rabbits, how many pairs of rabbits were there, those will produce a new pair of rabbits, we will get 2 here, right. So, and now what will happen is f4 in the 4th month. So, we will have see in the last month we had we were having 2 rabbits, right, 2 pairs of rabbits, not 2 rabbits, 2 pairs of rabbits plus, but then the rabbits which were there 2 months before, that means not the last month, last month, they will produce young ones now, right. How many, suppose there was 1 pair of rabbits in the last month, they will produce 1 more pair. So, that is 2 plus 1 3, right. Now, in the 5th month what happens is we have the total number of rabbits will be the 4th month, whichever number of rabbits are 3, right, those rabbits are still there, but then new rabbits will come which are produced by the pairs which were available 2 months ago, not in the 5th month. 2 months ago means f3 is the number of rabbits which were, so that is 2, f3 that is 2, this is 3 plus 2 is 5, right. So, this is what. So, then he was asking in the nth month how many rabbits will be there. So, this is a typical example of a recurrence relation. So, you know the nth month how you will find the number of rabbits is, you will notice that the number of rabbits will be equal to the sum of rabbits which were see when I say rabbits I mean pairs of rabbits. So, the number of pairs of rabbits which were existing in the n minus 1th month, that means f n minus 1 plus the number of rabbits which are newly produced. But because those rabbits which were newly born last month will not produce new rabbits now. So, only the rabbits which were existing last but 1 month, I mean 1 month before, I mean they need they need 1 month to grow up. So, the next to next month only, after they are born, next to next month only they will produce the young ones. So, therefore, we have to go to f n minus 2, that means in the last month there were f n minus 2 rabbits, pairs of rabbits, and each pair will produce a new pair. So, therefore, f n minus 1 plus f n minus 2 will be the new one. This is existing rabbits, pairs of rabbits, okay, existing pairs of rabbits, number of existing pairs of rabbits at the n minus 1 month. This were actually number of pairs of rabbits which existed at the n minus 2th month, but then what we are counting here is the pairs they are producing, right, because those rabbits which are existing at the n minus 2 are also existing at the n minus 1 month, right. So, they produce new ones. So, those extra count is this. So, that is how this is. Of course, you can argue that this is a cooked up problem, because of course, how do you make sure that one male and female rabbit together will always produce one male and female rabbit, right, and how do we say that there are only 2 rabbits produced by them. So, these are all there, but this is a problem which is proposed to illustrate this sequence. So, it is clear that we get the sequence f n equal to f n minus 1 plus f n minus 2 as the answer for this. This works for all n greater than equal to 2, right, because the first 2 f 0 we are just defining as 0, there are no 0. F 1 we have one pair of rabbits, and f 2 onwards we can add 0 plus 1. Because this pair of rabbits is not going to produce new ones now, but this 0 new ones are not going to come, and then f 3. So, this is producing new one and this is existing, right. So, this plus this, right, 1 plus 1 is 2. So, therefore, up from for n greater than equal to 2, this is true, and the initial conditions, we call this initial condition, f 0 is equal to 1. So, f 0 equal to 0 and f 1 equal to 1. These are the initial conditions, right. This is called the Fibonacci sequence, and you see this kind of relations are called recurrence relations. So, I assume that students are familiar with recurrence relation already. So, for instance, they have studied it in their algorithm course and many courses, but so we as of now we won't formally define it, but you should understand that this is a sequence of numbers. So, if for instance is a function of natural numbers, and this f n means the nth number in the sequence, right, that is obtained by combining certain numbers which had appeared before in the sequence. So, Fibonacci number takes the just previous number and one before, right, just two previous numbers are taken and added together, and then that is how the new number is produced, right. And now let us see, so because these Fibonacci numbers are very important and they appear in many problems. So, therefore, we will study them in little detail. So, this maybe it is a good starting point to study the recurrence relations, right, being one of the most important recurrence relation which we see in combinatorics. So, let us see. So, now we will take some of the properties of it. So, one first property we will study is what is the partial sum. Suppose we sum from the first 10 Fibonacci numbers f1 plus f2 plus up to fn. So, we have f0, but f0 is 0, therefore, whether we sum it or not is unimportant. So, we sum from f1, f2, fn, the first 10 terms, what will you get? So, this here we see that we always get fn plus 2 minus 1, right. This is the first formula we want, f1 plus f2 plus, maybe we can even write f0, does not matter, 0 plus, so up to f3 plus up to fn, then we will get fn plus 2 minus 1, minus 1, right. So, that's it. So, we can verify it for small values, for put n equal to 0, n equal to 0 means we are just taking f0, f0 is just 0. So, we are saying that, so the S0 is just f0, that is 0. Then we are saying that this is equal to fn plus 2, that means f0 plus 2 is f2 minus 1. f2 is what? f2 is 1 only, 1 minus 1 is 0, right. And for n equal to 1, we get f1, f0 plus f1 is the s1, right. That is 0 plus 1 is equal to 1. This is equal to f3 minus 2. f3 is how much? f3 is 2. This is 0, this is 1, this is 1, this is 2, right. So, we get 2 minus, sorry, 3 minus 1, this is 2 minus 1 is equal to 1. So, that is also correct. So, we have verified this formula for small values of n, and which seems to be working out. So, we want to give a general the proof for the general case, right. So, what we do is we do induction on n, this is the proof technique we use here, induction on n. So, how do we use induction on n? So, we have verified for n equal to 0 case, n equal to 1 case, even n equal to 2 case. So, we will assume that it is true up to n. Now, we will try to prove it for n plus 1, right. So, what we want to show is f0 plus f1 plus fn plus 1 is equal to fn plus 3 minus 2 is what, minus 1 is what we want to show, right. This is what we want to show. But then this one we can split it into up to here, that is, this is fn, right, up to fn up to here, and then this is what, this is f by induction hypothesis, this is fn plus 2 minus 1, and this is fn minus 1, right, sorry, n plus 1. So, this plus this minus 1, but this plus this is what, by Fibonacci recurrence relation, that is fn plus 3 minus 1, right. So, I am just combining these two terms, fn plus 2 and fn plus 1, that is the next term in the sequence, namely fn plus 3, and this minus 1 is, so this is so simple. So, we can prove it so easily by just simple induction. So, now let us look at the next formula. Fn is the next property of Fibonacci numbers we want to study. Fn is even if and only if n is a multiple of 3. This is also very easy to prove, so that we can verify first. So, for instance, Fibonacci numbers, if I write, so you start with 0, right, then the first number is f1 is 1, f2 is 1, so f3 is 2, then next is 3, next is 5, next is 8, and so on, right. So, this is f0, this is f1, this is f2, and so on, right. f3, so here is an even number, here is an even odd number, here is an odd number, here is an even number, right. Now, the first what happens is you have an even number, second is an odd number, right, these are by initial conditions are like that, The third will definitely be an odd number, because sorry, this is f2. F2 will be definitely be an odd number because we are adding an odd and even here. We will get an odd number only, but the next one is going to be an even number again. So we got f3 to be even as wanted. Now we want, so that next two numbers are always going to be odd, and after that we will get one even number. So here this is an even number. The previous one, by we have already seen this an odd number. So even and odd will give us an odd. So give us an odd number. This is an odd number, right? Now next also has to be odd. Why? Because now is an odd, and the just previous number is an even number. So even and odd is going to be an odd number for us, right? So now the next one we say that is again going to be a multiple of this. So this was f4, this is f5, this is f6, right? Now odd and odd will give an even, right? So this is the reason. So now it's very clear from here that now if we consider the next two numbers, they are going to be odd, because here even and even, this is odd, and here odd and even, this is going to be odd. Now the odd and odd will give an even, right? Two numbers odd, then even, right? This is the pattern. So Fn is even if and only if n is a multiple of 3, that's 0, 3, 6, like that. That's what we. Next we will consider the general formula. So formula for to compute Fn, we get a formula. We do not have to write the entire sequence, because as of now, if you want to find F10 for instance, what will you do? How will you find F10 or F100, right? So we will say that we start with F0 is equal to 0, F1 equal to 1, so then now F2 is equal to 1, so F3 equal to 2, F3 is F4 equal to 3, and F5 is equal to 5, and F6 equal to 8, and like that we can keep on writing till 100 by adding. Always we add the previous two numbers, write the next number, and till 100 we can go, but it will take a long time. So rather we would like a closed form expression for computing Fn. For instance, if you want to find Fn for n equal to 1000, right? So we can use that formula, right? That's what the next this thing. So we claim here that there is a formula, and the formula is given by this thing, 1 by root 5 into 1 plus, okay, this is 1 plus root 5 whole raised to n, so, sorry, 1 plus root 5 by 2 whole raised to n. This is a formula is written, the 10 we should have put a bracket here, so I'll just put it once again and write. The formula is this, Fn equal to 1 by root 5 into, so this bracket is missing here, 1 by root 5 plus 1 by 2 whole raised to n minus 1 by root 5 into 1 minus root 5 by 2 raised to n, right? So this will work for all n, right? This is, so here we needed bracket, here also we needed bracket, that's what is missing. This will work for all n. We can just try for small values of n. So for instance, we put n equal to 0, what will happen is, so this will become 1. So if you put n equal to 0 here, this quantity will turn out to be 1, this quantity will turn out to be, so we will get 1 by root 5 minus 1 by root 5, that will be equal to 0. So F0 will be equal to 0 according to this rule. So if you put n equal to 1, right, then what will happen? So then you get root 5 plus 1 by 2 here, minus 1 by root 5 into 1 minus root 5 by 2, then put n equal to 1. So you can take root 5, 1 by root 5 out, so it will look like 1 by root 5 into 1 plus root 5 by 2 minus 1 minus root 5 by 2, right? This 2 is common, so this root 5 cancels off, sorry, 1 cancels off, and then we get this 1 by root 5 into 2 root 5 by 2, this is 1, So, f1 we are getting as 1, right. So, like that it is working out even for n equal to 0, 1, etc. So, when you put bigger values, it is more difficult to compute. What you do is you, for instance, put n equal to 10, you expand it using binomial expansion, binomial theorem, and then we see that all these irrational numbers root 5 and all will cancel off, and finally we will get an integer number, positive integer, which is the value of fn, right. But how does this magic formula work, and why is it true? That is what we want to find out now. So, the technique is simple. So, this is what we should do. So, we will write, so for we know that for n greater than equal to 2, we have fn is equal to fn minus 1 plus fn minus 2. For the time being, we will assume that n is greater than equal to all the manipulation we are going to do now is kind of true only for n greater than equal to 2, right. We are assuming n greater than equal to 2 as of now, right. So, what do we do? So, we can rewrite it as fn minus fn minus 1 minus fn minus 2 is equal to 0. This is true for n greater than equal to 2, right. Because if you had taken n is 1, then we should have to worry about what is fn minus 2, that will be f minus 1, and then that is not defined, right. So, that is what this is only true for this is written only for n greater than 2, right. Now, what we do is to guess a formula for fn. So, how do we guess? So, we just think that this is some q to the power n, or q is some quantity, some quantity which we will figure out later, right. So, this is from experience, and then we try it out and see for what values of q this will work, or will it work at all, right. So, that means we will get something like, so we can by substituting we can get this is q to the power n minus q to the power n minus 1, this is minus q to the power n minus 2 is equal to 0, and this also for n greater than equal to 2 only. Now, assume that q is not 0, we will assume q not equal to 0. If q was equal to 0, the sequence will be 0 0 0 0, right. So, the q is not 0, right, because if you put q equal to 0, every number for every n we will get 0, f of n equal to 0. We know that that is not what we want, because we are trying to find a closed form expression for the Fibonacci sequence, which we know is not all zeros, right. So, therefore, q is not 0, q to the power n minus 2 is also not 0. In the worst case, in any case, even because n is at least 2, that q raised to 0 can be 1, but whatsoever. So, therefore, for any n we can divide by q to the power n minus 2, divide by both sides, right, divide both sides by q to the power n minus 2. So, what do we get? Q square minus q minus 1 equal to 0 is what we get. So, that q to the power n minus 2 was common to everything. So, we divided it off on the 0 side, so on the other side also. Now, what is a possible value of q? Is there a possible value of q? You know, there is a quadratic equation, you know, x square minus x minus 1 equal to 0. If you can find the solution for this thing, and that will work for that will be a that can be taken as the value of q. And you know, this by using the minus b plus or minus root b square minus 4ac by 2a formula, right. For instance, we know that. So, you remember that ax square plus bx plus c equal to 0, the roots are x equal to plus or minus b minus b plus or minus b square minus 4ac by 2a. So, here you know a equal to 1, b equal to minus 1, is not it, b equal to minus 1 and c equal to minus 1, c equal to minus 1, try putting it. So, we get 1 plus or minus 1 minus 4 into a is 1, c is again minus 1, this will be plus, and divided by 2 into a is 1 2. So, this is root 5 here. So, root 5 we have 1 plus root 5 or 1 minus root 5, there are two solutions, 1 plus root 5 by 2 is a solution and 1 minus root 5 by 2 is a solution for this thing. So, what it means is, so you can take the q is equal to 1 plus root 5 by 2 or you can take 1 minus root 5 by 2. In both cases this recurrence, for instance q to the power n equal to q to the power n minus 1 plus q to the power n minus 2 will work, right. This is true. So, it will work. So, this would be a general solution, but the point here is that we have only considered the recurrence relation, we have not considered for instance the two values, initial values, namely 0 is equal to 0 and f1 equal to 1, we have not considered, right. We have to make sure that this also works, make sure that this is consistent. So, now for instance if you take root 5 minus 1 by 2 as q and you just put q to the power 0, right. So, if this was the value actually f0 is equal to this, I am just putting n equal to 0 here. So, then this will be 1, right, but we know f0 has to be 0. So, there is something wrong about it. So then what can we do? So, we have to somehow adjust for that, adjust to make sure, we have to make sure that the initial values are also satisfying this thing. Otherwise what happens is, so this it is true that if I take fn equal to q to the power n, that will satisfy the recurrence relation, but it will not give the Fibonacci sequence, because initial values for q to the power n with q is equal to say root 5 plus 1 by 2 whole to the power n, right. So, when I put n equal to, because recurrence relation when you start with the correct initial value only we will get that same sequence, we start with another initial value we will get definitely a wrong thing, right. So, for instance here we will, if you put n equal to 0 we are getting only f0 is equal to 1, and when you put f1 n equal to 1 we are getting root 5 plus 1 by 2. So, if you had started with these two initial values, definitely this formula will give the correct solutions, right, because that is what it says. So, qn is actually equal to qn minus 1 plus qn minus 2, right, for n greater than equal to 2. So, if right. So, but then how will you make sure that initial value is met, right, because otherwise we will not get the Fib, we will get some strange sequence here. If you keep on substituting this thing you will get a strange sequence, we will not get any the Fibonacci sequence that we are looking for. The same is true if I try 1 minus root 5 by 2 whole power n, right. So, when n equal to 0 we are again getting 1. So, f0 is equal to 1 is what we are getting. Similarly, when I put n equal to 1 we are getting only 1 minus root 5 by 2, it is not even an integer. So, definitely the next one will be, so this square of this thing, it is not the Fibonacci sequence, then how will you get it? So, what we observe is that, so while the recurrence relation is satisfied, for instance, is Fn is equal to Fn minus 1 plus Fn minus 2 will be satisfied if you take Fn equal to q to the power n for q equal to root 5 plus 1 by 2 or q is equal to 1 minus root 5 by 2. We have also other other expressions which will satisfy this thing. For instance, if I had taken Fn equal to c into some constant into 1 minus root 1 plus root 5 by 2 raised to n, then also this will be satisfied. Why is it so? You can just verify it. For instance, what we get is Fn equal to c into q to the q, so we say root 5 plus 1 by 2 to the power n minus 1 plus c into root 5 plus 1 by 2 to the power n minus 2, right. We can take c as common, c into so this is root 5 plus 1 by 2 whole power n minus 1 plus root 5 plus 1 by 2 whole power n minus 2. But we have already seen that these two add up to c into, because that q to the power n is equal to q to the power n minus 1 plus q to the power n minus 1. So, when you put q is equal to this value, so we will get this as c into root 5 plus 1 by 2 whole power n, right, that is true. So, the c also comes. So, if we had defined Fn as c times some constant times this root 5 plus 1 by 2 whole power n also, that recurrence relation is indeed satisfied. Same is true that if you had defined Fn as c into some 1 minus root 5 by 2 whole power n, then also it will recurrence relation will be satisfied, right. And more generally, we could have defined Fn as some constant times c1 times 1 minus root 5 by 2. So, 1 plus root 5 by 2 whole power n plus some constant, some other constant times 1 minus root 5 by 2 whole power n. You substitute in, for instance, you take what is Fn minus 1 plus Fn minus 2 according to this definition. Then what happens is this will be c1 into this quantity, same quantity 1 plus root 5 by 2 n minus 1 plus c2 into maybe, yeah. So, what happens is you should do this calculation and see that I need a different page here, maybe I will write like this. So, let me try calculating Fn minus 1 plus Fn minus 2. This will be equal to c1 times this I am expanding first, right, c1 times 1 plus root 5 by 2 whole power n minus 1 plus c2 times 1 plus 1 minus root 5 by 2 whole power n minus 1 plus, then again I expand this. So, c1 times 1 plus root 5 by 2 whole power n minus 2 plus c2 times 1 minus root 5 by 2 whole power n minus 2. Now, we can combine the terms together. For instance, I can take c1 into 1 plus root 5 times n plus 1 and 1 plus root 5, these two terms I can combine. So, this term and this term I combine, that is c1 times this plus this, which is essentially, we know that c1 times, that is going to be c1 times 1 plus root 5 by 2 whole power n, because we know that q to the power n minus 1 plus q to the power n minus 2 is q to the power n when q is taken as 1 plus root 5 by 2, right. Similarly, these two terms I can combine, this term and this term, right. This is c2 times 1 minus root 5 by 2 raised to n minus 1 plus 1 minus root 5 by 2 to the power n minus 2, that we know is 1 minus root 5 by 2 to the power n. So, this is essentially our definition of Fn also, right. This is the way we have it. So, they are adding up to Fn, this 2 are adding up to Fn, Fn minus plus 1, Fn minus 1 plus Fn minus 2 is giving Fn. So, indeed we can define, because we have two solutions. So, we can take the general solution as C1 times that two solutions, first solution, and C2 times the second solution, right. The first solution is 1 plus root 5 by 2 whole power n, the second is 1 minus root 5 by 2 whole power n. The next thing is, okay, if this is, what is the use? The use is only that I have not defined C1 and C2 here. I can select it, any value I can select such that the initial conditions are met. What are the initial conditions? The one is F0 is equal to 0, which means when I put n equal to 0, I will get C1 plus C2 is 0. This is what we get. The second is F1 is equal to 1. So, when I put n equal to 1, I get C1 into 1 plus root 5 by 2 plus C2 into 1 minus root 5 by 2 is equal to 1. So, this is simultaneous equations. C1 and C2 we want to find out such that these two conditions are met, C1 plus C2 is equal to 0, and C1 times 1 plus root 5 by 2 plus C2 times 1 minus root 5 by 2. We know that this can be solved, right. So, you can try to solve it, and then we get C1 equal to 1 by root 5 and C2 is equal to minus 1 by root 5. So, I am not wasting time on solving it as such. So, finally, our formula will be Fn equal to 1 by root 5 into 1 plus root 5 by 2 whole power n minus 1 by root 5 into 1 minus root 5 by 2 whole power n. So, the good thing here is when n I put n equal to 0, I get the correct value, F0 will be equal to 0. That is the way I have adjusted C1 and C2. Similarly, when I put n equal to 1, I will get F1 equal to 1. That is the way I have decided my constant C1. I could have selected C1 and C2 as anything, but because there are two initial values to be met, I carefully selected C1 and C2 so that those things are met. But once these F0 and F1 are met, the rest of the things are taken care of by the recurrence relation, namely Fn is equal to Fn minus 1 plus Fn minus 2, because for the expression we selected this is valid, right. So, Fibonacci numbers will come. We will discuss in the next class.